Yeah, fancy title. Sounds a bit like a new episode of Star Wars, but it's just a bit to get your attention.
May the force be with you.
May the force be with you. So, but about the problem we are facing here is GNSS orbit modeling means nowadays that we have numerous GNSS satellites in orbit, about 100 satellites operational and another 170 that have been launched in the past. And we have dozens of different spacecraft types. We have not just types, different types, generations of satellites, we also have subtypes of satellites. So if you want to create a physical-based analytic model for each of these groups of satellites, you would need to have really detailed knowledge of the characteristics of these satellites. You also would need to have accurate Earth albedo and infrared models, of course. And the problem with this data often is that it is often inaccurate or even incomplete, like for Baidu, or simply unavailable at all. So, quick overview about force modeling, non-gravitational force modeling. We have four main forces here. First, most important, of course, solar radiation. We have thermal radiation, second place, the Earth radiation, and antenna thrust. And of course, you have shortcomings if you try to model these forces. That's why we typically solve for additional empirical parameters, either in a sun-fixed or spacecraft-fixed frame. So our approach is very similar to the one that JPL invented more than 20 years ago. We do a dynamic long fit arc fitting to precise orbit SP3 data. We represent the force as a Fourier function of the Earth-satellite-Sun angle, and then we solve for these Fourier coefficients together with orbital state, y-bias, and then some long-track parameters. And the key thing here is that we do this for a longer time period, at least 1 year, and combine the coefficients at normal equation level to create a set of robust satellite or even block-specific models. The advantages of this physical-based models are obvious. There's no need for a dimension of the spacecraft or properties. They are very efficient, easy to implement. It's just 3 lines of code, basically. They reflect the satellite and orbit behavior. They are basically all in one. All 4 forces are lumped together, and there's no need for an ERP model anymore. But there are also disadvantages because these parameters they tend to absorb other effects like Earth rotation or geocenter variations. This is how the model looks like. We have basically, for all group satellites, we have the same set of coefficients, 12 coefficients, satellite-specific. Unlike for Galileo, we have decided to do a group-specific model. So we have 4 groups of satellites, 1 parameter less, only 11 parameters. And so this is basically the two different model equations. And this slide shows you how the force looks like as a function of the Earth-Sun angle for the different 5 GNSS systems. Interesting slide, I think, because it shows how different the forces really look like. But there are also quite significant differences between satellites of one block and then one manufacturer. For instance, if you look at Baidu, it's up on the upper right side. There are obviously, it's not just one group of satellites, there are more than 5-6 groups of satellites. So you have to see how to treat them, and we decided to do it satellite-wise. One could also argue that some can be put together into one group. And well, another interesting fact is the GPS Block 3 satellites shown on the left plot is they are for Block 2, they behave quite the same, but the Block 3s are looking quite different with respect to each other. So they apparently have a different surface design, or I don't know. And so what we've done to evaluate these models, we generated 24-hour ARC solutions over 1 year of data based on a 150 station global network, generated 3 solutions. Same data sets, only difference being the force model applied, radiation force model. So first test candidate, it was the Econ 1 model without any a priori valid model. then the ECOM2, again without any a priori, and then finally ECOM1 together with our Fourier model. And then we evaluate these orbits by typical performance matrices like narrow-lane residuals, empirical radiation pressure estimates, SLR residuals, orbit overlaps, or prediction errors. And so this is the narrow lane, a bit about this. So this is just the fractional part of the unresolved double difference narrow lane ambiguities. This is a nice, strong indicator of orbit model accuracy. The background of this is that there's basically the orbit error does not cancel out in double differencing. So the better your orbit model is, the smaller these narrow lane fractionals should become. And you see that for these three test candidates, three different histograms here, that orange is the model with the Fourier included, and that's clearly has the smallest narrow lane fractionals. And I have another slide on the fractionals. We also typically do is to quantify the quality is to compute the so-called kurtosis. That is a measure of the distribution's tailedness of the histogram. And again, you see here that the highest kurtosis, so high kurtosis means better. High kurtosis for the Fourier-based model, it's in orange, and lowest basically for ECOM1 alone. So there's a factor 2 difference between orange and green, and there's even slight improvement compared to ECOM2. The ECOM parameters we solve for, without any a priori model, you have typically large signature in the estimates, particularly the cosinus term. There are kind of a gull-wing pattern in the B0 and the BC term for certain satellites. With the model applied, obviously these estimates are getting much smaller, much less systematic. There is a RMS reduction by a factor of 3 to 4 even. This is shown here in the table below, particularly for B0 and BC. We have really a large improvement with the model applied. I also have another dedicated slide to that. We have here the estimates, B0 estimate as a function of beta angle for the 5 different systems. What I said at the beginning, you have this pattern, this signature, also for block 3. Kind of a gull-wing pattern. Most striking, certainly for Baidu. There are 2 Baidu satellites that are out doing weird things here. They have also a very strong signature, and at least when you do, if you don't apply anything a priori, whereas with the a priori model applied, you get these orange, pretty flat estimates. Yeah. Also, there's one Galileo IOV satellite that has a bit of a signature. And yeah, and then we have also the BZ estimates. Again, for Galileo, there's a big signature without any model applied. And with model applied, it's rather flat. So that's the good sign for the model. There's also strong reduction in SLR residuals if you have the model included, especially for Galileo QZSS. I have here the mean bias of the SLR residuals, also the standard deviation, again per system, obviously without GLONASS, but for Galileo and for Baidu and for QZSS. And again, we have about a factor of 3 to 4 reduction. If you look at Galileo, 18 millimeters with ECOM1 only, and with Fourier applied, about 22 millimeters for FOC, for IOV, same for Baidu, and even also same for QZSS, and some smaller reduction for Baidu, for the Baidu, 2 different groups of Baidu satellites. Then we have orbit differences, what we call orbit overlaps, the comparison of consecutive arcs at the midnight epoch as a measure for precision of the orbit, or internal consistency, if you like. And again, the ECOM1 with the Fourier clearly outperforms the ECOM1, again, particularly for Galileo and QZSS, but also for the other constellation, and it even is a little bit better than the extended ecom 2. So a similar plot that shows the prediction error. Again, same picture here. So there's a predicted orbit, and I take the epoch, the position at the 24-hour epoch, compare it against the reference orbit, and again, a very strong reduction with the Fourier applied compared to ecom alone, and it's even slightly better than ecom 2. Again, particular for Galileo and QSSS, but also for the other systems. And so in conclusion, this is we built a very simple radiation force background model for all GNSS, tested that thoroughly. We compared the model against the ecom only approach without a priori. Turns out it is superior to ecom 1, which is not a bigger surprise. In every respect, but it's really clearly better than just ecom 1 in terms of all kinds of metrics, SLR residuals, ambiguity resolution, overlaps, and it's even on par with, or even surpasses, the ecom 2 results. There is some future work. We're going to certainly have to refine the model, particularly for this one, these strange Badu satellites. We're going to compare, of course, the results against public boxwing models, and also have to improve the eclipse handling. In particular for Galileo, this is needed. And then finally, we're going to make these models available to everyone, free of charge. And so you see the future. The story isn't over yet. The invisible is tamped, but it's not yet defeated. Thanks.